Hey everybody, so today's video will show you how to use Beer's law to determine solution molarity. And you'll remember molarity is defined as the moles of solute per liter of total solution. All right, so this is Beer's law is helpful if you have a solution and you know its identity, you know what it is, you just don't know how concentrated it is, and you don't have any information about how it was made, how many grams were used, how many moles were used. Okay, Beer's law takes advantage of the fact that if you shine light through a colored solution, some of that light will be absorbed by the colored molecules in the solution. So this instrument is called a spectrophotometer, and inside is a light source. On the outside is a dial where you can adjust the wavelength of light that is traveling to the solution. And then the solution is inserted in this little test tube called a cuvette. And the more concentrated it is, the darker the color will be, and the more light will get absorbed. So you might only see a little bit of light transmitting through for this example. All of this light shone into the solution, but much of it was absorbed by the colored molecules. Now the machine measures how much gets transmitted through, and then it converts that into how much light got absorbed using this relationship. Absorbance is equal to the negative logarithm of the transmittance. So the transmittance can be measured, and then the absorbance is calculated. And then there's a spot on the outside of the machine that would tell you that absorbance. Now let's just look at another example of the same stuff. This is also potassium permanganate, but clearly this one is more concentrated and this one is dilute. So when you put a more dilute sample into the machine, the light shines to the sample and not as much is absorbed, which translates into a lot more gets transmitted. Okay, so again, the machine's reading, oh, this time a lot transmitted through, so not very much was absorbed. And you would get a smaller absorbance reading for a lower concentration. High concentration would give you a high absorbance. Okay, now the actual statement of Beer's law looks like this. Beer's law, also known as the Beer-Lambert law, but almost everybody just calls it Beer's law, tells us that absorbance is equal to ABC. C is the concentration or the molarity. So as this number C gets bigger and bigger, absorbance gets higher and higher. These two parts of Beer's law, the A and the B, represent absorptivity constant. Notice I put constant in quote marks. That's because this number is only constant for a given substance. So we were talking about potassium permanganate. It has a certain absorptivity constant, but then if you did another experiment with the bluish green copper chloride solution, that would have an entirely different absorptivity constant. B is the path length. Let's talk about that for a minute. So the cuvette that you put into the machine has a fixed width, and that is literally the length of the path that the light must travel through to get to the other side. So notice that I've got a second sample here. It's the same concentration, but I'm using a wider cuvette with a longer path length. Can you just intuitively see that in this wider sample with a longer B path length, there would be more colored molecules that this light would bump into and have a chance to be absorbed by. So the longer the path length, the greater is going to be the absorbance. So all of those pieces are important in using Beer's law. Now, one way to calculate concentration is just to flat out use this equation, rearranging it for C, and plugging in your values. Now, measuring the absorbance is easy with the spec 20, but you would have to know the value of A, the constant, and you would have to know the exact path length in centimeters. If you did know all of that, you could calculate the concentration. Truthfully, we don't use Beer's law in that way very often. What's much more likely is for us to plot a calibration curve. So let me show you an example. This is a curve in which potassium permanganate was made up in a number of different molarities. So you have to take the time to make, very carefully, several solutions with different molarities. You set the machine at the best wavelength, and then one by one, you put these samples in and you measure the absorbance. So here was a fairly dilute solution and I measured its absorbance. Plot that point. Make a new solution of a different molarity, measure the absorbance, plot that point. You can see that this calibration curve is a straight line. That's because there is a direct relationship between these two variables. Well, once you've got your calibration curve plotted, then you could answer a question like this. Let's suppose you had a sample of the same stuff. You're going to test it at the same wavelength, and you measure its absorbance to be 0.75. So you can use this calibration curve. We'll find absorbance 0.75, be right about here. And then we're going to draw a straight line over until we hit the curve, the calibration curve, and then we're going to drop down and read the molarity. So that's a really simple way to find the molarity, the concentration, if you've got a calibration curve already made up. There is a third way that Beer's law is helpful to us, and that involves setting up a ratio. So let's take a look at Beer's law again, and let's divide both sides by C. Now these are going to cancel out, and that gives us this form. And remember that in a series of experiments, that constant is going to be the same, and your path length in your cuvette, you're going to stick with the same size cuvette, so B will be the same. So this product right here is some number, which is constant. So I'm going to say that if I have concentration 1, and I measure its absorbance, I'm going to call that absorbance 1. That ratio is equal to this constant AB. Then I could take a second concentration, measure its absorbance, I'll call that A2, and that quotient will still be equal to this same AB. So since this ratio is equal to AB and this ratio is equal to AB, then we have those two values equal to each other. So that's the ratio that can be helpful in a problem like this. Let's suppose you don't have a calibration curve, but you do have this table of data. So you have 3 different concentrations that were made up, and their absorbances were measured. Notice that as the concentrations got bigger, higher, the absorbance also got higher. All right, so now let's suppose you obtain a 4th sample and you put it in the spec 20 spectrophotometer and you measure its absorbance to be 0.316. Well, looking at this data table, that absorbance falls between these two, so we would infer that the concentration is going to fall between these two numbers. All right, to use this ratio, this proportion, we're going to pick a set of data that has an absorbance close to this one. So I'm going to pick this set right here. And that's going to be my A1 and my C1. A1 is to C1 in the same way that my new absorbance, my mystery absorbance, is to its concentration. Having set up that proportion, then I simply solve for C2, and here's my answer. And let's do a common sense check. Is this concentration, in fact, between these two? And yes, it is. Okay, so guys, again, Beer's law gives us 3 different ways to calculate solution molarity. We can use the equation as is if we happen to know the A and the B, or we can plot a calibration curve and then measure the absorbance of our new substance and read its molarity from the curve. Or thirdly, we can set up a ratio from a set of data. Okay, I hope that helps.